Okay. All right, here's what I want to do real quick today. I want to do a little review. A lot of this is review too. So everybody put all your stuff away, phones and all that good stuff. Get all those away. Uh, we're going to look at inverses, and you've done some stuff with inverses in the past. We're just gonna add to that. Let's remind ourselves though. It's probably been a while for Algebra 1. Since you talked about inverses, let's remind ourselves what it means to be an inverse relation. So when we talk about inverses in math, inverse relations, and a relation, remember, is just anything that we could have an equation for, right? Anything that fits some equation. I could put in values of x and solve for values of y, right? Usually we deal with functions, things like lines or quadratics or polynomials. But it could be other things too. They could be square root functions, cube root functions, could be anything. Now, an inverse relation maps the output values back to their original input values. So this means that the domain of the inverse relation is the range of the original and vice versa. So we're just flipping the domain and the range. If I start off with some relation and I want to find its inverse, all I'm essentially doing is taking the x and y values from the original relation and just flipping them. So the x values become the y values and the y values become the x values. Okay, so we can see that like this. Let's say we've got some relation where I've got a certain domain. X could have these values. And this is this is a discrete one. This is a little different than most of the ones we'll deal with. This is one where x has only, instead of having a range of different possible values, x has only 5 discrete values. If that's the domain of the original, then the range of the inverse would be those same numbers, only they're y values, right? Okay, and the domain of the original becomes, the range of the original becomes the domain of the inverse. So what used to be our y values now become our x values. So if we look at these as individual ordered pairs, in the original relation, we had a point with coordinates -2, +4. Well, in the inverse, we've got a point with coordinates x = 4, y = -2. Okay? Now watch what happens if we plot these things. There's a relationship between the graph of the original and the graph of the inverse. Okay, so the blue dots represent, those are the points that represent the original relation. Now watch if we graph the inverse, what happens. Okay, there they are. Now there's the first one. Notice what's happening here. When I swap the x and y values, so we'll take this first one, instead of having an x value of -2 and a y of +4, it's going to have an x value of +4 and a y value of -2, right? Look at the relationship between those 2 points. They are just reflections of each other over this diagonal line through the origin, which is just the equation of that line is just y = x, right? mx plus b, well, the slope is 1, and the y-intercept is 0. So if we know, if we plug that stuff into y = mx plus b, don't we just get y = 1x plus 0, or just y = x? So that's the equation of that line of reflection. Okay, there's the other point. Now this guy's already on the line of reflection, so what happens to a point if we reflect it and it's on the line of reflection? It just stays there. Okay. Right, but you see that relationship? Okay. All right, now I'm going to give you, this is not in the book, but I'm going to give you a recipe for graphing an inverse. It's an easier way to do it. It's actually kind of hard to visualize reflecting something over a diagonal line. It's simple to do vertical lines and horizontal lines, but diagonal lines are a little tougher. You can always do this though. If I start with some relation, I can do 2 transformations that very easily give me the inverse. If you take the original graph, you might want to write this down, or just listen very closely. If you do 2 things, if you take the original graph and you rotate it 90 degrees counterclockwise, and then reflect it around the y-axis, that does the same thing. Only that's a little bit easier to do, I think. Okay, so if we took this blue one and rotated it 90 degrees, for example, wouldn't this point right here, if I rotate it 90 degrees, it's going to end up kind of down there by rotating it around the origin 90 degrees. And then if I take that point and I reflect it over the y-axis, it ends up right there.
Wow.
See how that works?
Yeah.
Okay, we'll do that again. When we get to some of these other graphs, we'll do that again. Okay, but that's an alternative to reflecting it over the line y equals x. Just a 90 degrees counterclockwise rotation, and then a reflection over the y-axis. Okay. Okay. So we swap the x and the y variable, or x and the y values, and that gives us this symmetry about the line y equals x. Okay, so how do we go about finding the values? How do we go about, or finding the inverse of a relation? Okay, if we start off with something like y equals 2x minus 4, if that's my original relation, and I want to find the inverse, do you remember, you probably do you remember what the steps are? Okay, so we start with this. Whoops. Y equals 2x minus 4. If I want to find the inverse, here are the steps. First, we write it in terms of x's and y's. It's like if we started off with f of x equals something, write it in terms of, make that a y. This one's already done. It's already written in terms of y. Then, you just swap the x and the y. I'm going to change colors so we can keep track that we've done that. So this becomes an x, and that becomes a y. And now what do I do? Well, okay, I'm going to add 4, and why am I doing this? What am I trying to do now? Solve for the new y. That's it. Right, solve for the new y. So I'm going to solve for this guy. So I add 4, divide both sides by 2, and I get my answer. Y equals x plus 4 over, no, I can't do that. X plus 4 over 2. If I want to, I could split that into 1/2 x plus 2 if I want to break it into separate fractions. And that might be good if I want to write it in mx plus b form. But then that probably is okay too, right? Yeah. And I've got my new, this now is the inverse. Okay? So we write the original in terms of x's and y's, flip the x and y, and solve for the new y. That's our recipe for finding an inverse. Okay? Yeah, it's not practical. But I know you've done that. It's probably been a while, but I know you've all done that. And there we go. Right? Okay? Okay, so a couple things in about inverses. Now, functions f and g are inverses of each other if these two things happen. This is our test. If we're given two functions and we want to know if they're inverses, we have to do both of these things. What it means to be an inverse, the definition is that we switch the x and the y. But if you think about it in terms of kind of how the two things are related, inverses are sort of opposites of each other in a way in math. Inverses undo each other. So if, for example, if f and g are inverses of each other, and by the way, that doesn't mean that f is the original and g is the inverse only. It goes both ways. I could also say, I could think of g as being the original if I want to, and f being its inverse. It's a two-way street. Just because we happen to start with f doesn't really mean that it's any better than g or any different. If g is the inverse of f, then f is also the inverse of g. Okay? So if those are inverses, then they have to undo each other when I superimpose them, or when I take f of g, when I write a composition of the two. So if I actually evaluate the function f at g of x, so if I'm putting g of x into the function f, I have to get back the answer x. In other words, the f has to undo the g. And vice versa. If I put the f of x inside the g of x, I'm taking g of f of x, that also has to undo the x. Okay? If that's true, if both of those things happen, then they're inverses of each other. And the way we could write g then is f, it looks like you're saying to the negative 1 power, but you're not. That's just our notation for an inverse. What that means the inverse of f of x. Or people sometimes say f inverse. Okay? Let's look at an example of this. Okay, so for example, if I want to verify, I'm told that f of x equals 2x minus 4 and g of x equals 1/2 x plus 2. If I need to verify that, I have to show that f of g of x equals x and g of f of x equals x. Now think about this for a second here. If f of x equals 2x minus 4, let's try a couple things here. What is f of 2? Say it again. 0. And how'd you get that? Okay, because I'm plugging 2 in for x, and so whatever used to be an x has now become a 2, right? And so I get back the value 2 times 2 is 4 minus 4 is 0. Okay. What is f of a? 2a minus 4. Right? Because whatever used to be an x, now I'm plugging in an a. Okay, what is f of g? What's my pattern here? Whatever I plug in for, yeah, it's just going to be 2g minus 4. Now let's just change that ever so slightly. Instead of calling that g, let's call it g of x. So f of g of x would equal what? Okay, good. 2 times g of x minus 4. Well, what's g of x? It's right there, right? That's g of x. So that's what I would have to plug in right there, right? I'd have to get 2 times. Now I got to put that in parentheses. That's a quantity, isn't it? I can put all that stuff being multiplied by 2. So it's 2 times the quantity 1/2 x plus 2, because all that stuff is g of x, right? Minus 4. Okay, now what's the order of operations tell me to do here if I'm simplifying? Okay, inside the parentheses first. So I can't, those aren't like terms, so I can't combine those, but I tried. Can't do anything in the parentheses, right? So after parentheses comes exponents. No exponents. We can skip that too. Multiply, divide. What's that mean? Okay, I got to distribute the 2, right? Distributing is multiplied, so I'll take that 2 and distribute it to both of those 2 terms. So what's 2 times 1/2 x? That's just x, isn't it? 2 times 1/2 becomes 1, so that's just x. Plus 2 times 2. Okay. Good. So I get x plus 4, and then I get this minus 4 at the end. X plus 4 minus 4 is? Yeah, those cancel, don't they? So I just get x. Yeah, so we got it. So f of g of x equaled x, right? So far, so good. Now I got to try it the other way. They both have to work for these to be inverses. Okay, so let's try g of f of x. Now what's g of a? If g of x is 1/2 x plus 2, what's g of a? remember, all the function is just a machine that tells you what am I doing to the inputs. If I input something, call it x, it looks like I'm just multiplying that thing by 1/2 and then adding 2. So g of a would be 1/2 a plus 2. So then what's g of f of x? Good, so 1/2 times f of x plus 2, and what's f of x? Well, there's f of x right there, right? So what used to be the f of x, I have to make the quantity 2x minus 4, right? So I get 1/2 times 2x plus 4 minus 4, whoops, sorry. Okay, and so if I distribute that 1/2, what am I going to get? 1/2 times 2x is, yeah, just 1/2 times 2 times x. 1/2 times 2 is 1 times x is x, right? 1/2 times 4, yeah, so x minus 2 plus 2, what's that equal to? X. So it worked, right? So it worked both ways. F of g of x equal to x and g of f of x equal to x, and so we got it. Okay. Just in summary, that's what we did. Both times f of g of x gave us x, g of f of x gave us x, and so they are inverses. Okay? Now, finding the inverse of a power function. Okay, this is a little bit trickier. You gotta be a little careful with this one. So let's take something like this. If f of x equals x squared, let's go through our steps. Now, what's our recipe for finding an inverse? What do we do first? Okay, good, but before we can switch x and y, we got to write this in terms of x and y. So we're going to turn the f of x into a y, so I get y equals x squared, right? Now I flip the x and the y. Okay, is everybody getting this? Everybody getting this? Jack, you getting this? Okay. All right, so x equals y squared. Now, how am I going to solve for y there? I square root, okay? So then I'm going to get y equals square root of x?
Yeah.
Okay, forget something though.
Plus or minus the square root.
Plus or minus the square root of x, okay? Now, why do I need that, plus or minus there? Let's take a quick look and see. Why would I need that? If I pull up, let's look at these inverses together real quick. Well, here, I'll tell you what, how about if we just graph it? I won't use the graphing calculator, we don't need to. So if I graph the function, whoops. Y equals x squared, what does that look like?
A plane.
What does that look like? Y equals x squared. Parabola. Parabola. And this is just our kind of our basic normal parent function parabola. This is just the one that goes like that, right?
Yeah.
Okay, everybody agree?
Mm-hmm.
Okay, now let's make a prediction what the inverse should look like. Okay, we gotta reflect this thing over the line y equals x. But to do that, it's actually almost easier. Let me do something here. Oh, I'm gonna be really tricky. Watch this.
Oh,
Yeah,
don't do
this-
it. Don't do it.
Oh, this is gonna be so tricky. You know what? You think you know what I'm doing?
I know for a fact that you do. I think you do this so geometry class.
Okay, so I gotta do that. Okay, let's go ahead. Oh man, this is So if I take this guy, I told you there's two things we can do to this, right? If I wanna make a reflection over the line y equals x, it's easier to rotate 90 degrees. Okay, so let's do that. So if I take this guy, whoops. If I take this guy and I reflect it, or if I rotate it 90 degrees, I gotta move that a little bit too, don't I? To get that, it'd be like right there, wouldn't it, if I took this whole thing and rotated it down? Everybody agree? Now if I wanna reflect that, just a bit more right there-ish, okay? Now if I wanna reflect that over the y-axis, there's a way to do that too. I got, oh man. Tools, math tools. Okay, I should have done that before, but I know there's a way I can reflect it. Hey, give me 1 second. I thought I had this. Oh, this is. I've never gotten to play with this one yet, so I'm just kind of excited about this. Yeah. What do I do? Oh, here we go. I got it. Transform. Right here. You gotta hit this first, though. Yeah. I got it. There we go. So I want to mirror y-axis. Okay, now I just need to scoot it over, though. It's got to go. Uh-oh, wrong one. So it ends up like right there. Agreed? Mm-hmm. Okay. We want to. Let's make this red, though. Okay, and let's make this one like gray, because that's just sort of the in-between one. Okay, everybody see that?
So I have a question.
Yeah.
So you know how you want to rotate it 90 degrees counterclockwise and then reflect it?
Yeah.
Why don't you just rotate it 90 degrees clockwise?
Because that won't always work. It's different. That won't always work. Yeah. In this one case, it's a good question. In this one case, it would have worked, but generally speaking, it doesn't work. Generally speaking, it doesn't. You got to rotate counterclockwise and then flip. Okay, now everybody sees how that worked, right? We started blue, we rotated 90 degrees counterclockwise to get gray, and then we reflected over the y-axis to get red, right? So the red should be the graph of the inverse. Now, what's the inverse, though? Well, the inverse is, whoops, yeah, x equals y squared, and we've just graphed that. But the problem with that is, now look closely here, is the inverse a function this time?
No.
Okay, don't lose, now's not a time to get distracted. You gotta really watch this closely. Everybody focus on this. Is the red graph a function?
No.
How come it's not? You're right, it's not.
Because you can cross over 2 points.
Okay, it fails the vertical line test, doesn't it? If I pass a vertical line through the red relation, it's gonna intersect it twice, and so it's not a function.
So,
Now, if I solve this thing like we did for y, we got two answers. We got y equals plus or minus the square root of x. Well, what do you suppose it looks like if I graph y equals positive the square root of x?
you're going to get the top part.
That's right. Y equals plus the square root of x looks like that. If I graph y equals minus the square root of x, I'm just flipping that over the x-axis, and there's the bottom. So that's really pretty cool that it does that. Now think about this, what the math gods have done for you here, when you flip the x and the y and solve for y, they have conveniently broken this up into the two functions that make up the inverse relation. Because if I take these one at a time, if I take just the green one, y equals the square root of x, by itself, that is a function, isn't it? That does pass the vertical line test. Minus the square root of x, by itself, also passes the vertical line test, right? So that's why we need that plus or minus on there, okay? Now, these weren't, a lot of times we want to deal in terms of inverse functions and not inverse relations. We'd like to pick a starting relation and an ending relation that are going to give us functions in both cases. The original blue relation passed, now this is really important here, the original blue relation is a function, isn't it? y equals x squared is a function. It passes the vertical line test, but its inverse was not, because it failed the vertical line test. Let me ask you a question here. Could you have predicted, is there some kind of other test, not the vertical line test, but is there some kind of other test we could have done on the blue original to predict that it was going to, that the red one was going to fail the vertical line test? Horizontal line test is it. Okay? If the original relation fails the horizontal line test, then that means that the inverse is bound to fail the vertical line test. Okay? So what does that mean? It doesn't mean that the original is not a function. All it means is that its inverse is not going to be a function. Right? Does that make sense?
Yeah.
Okay? So if we wanted to make two functions here, we would have had to have started with only half of that blue one, wouldn't we?
Yes.
Right? Because if I had just started with, say, well, what if we had just started with the right half of this one, just the orange one? Well, what would that have been? It would have been y equals x squared, but we only would have taken x values that are greater than or equal to 0, right? We would have thrown away the rest and only taken this part. If we had taken the x values, the graph of the original blue function only for the positive x values, then when we reflected that, wouldn't we have gotten this green answer?
Yeah.
Everybody agree? Okay. So the fact that the original x values were positive, isn't that convenient that that gave us the positive y values in the final version? That gave us the plus, right? Now what if we had only taken the left side of the original? If we'd only taken the blue part? Well, the blue part, that's only the part here where x is less than or equal to 0, right? Everybody see that? Okay, which part would that correlate to? Well, if I reflected that over the line y equals x, wouldn't I have gotten this pink one down here?
Yep.
Right? Okay, now think about that. So if we flip the x and the y, we would have gotten x equals y squared, but what would that have become? That would have become y is less than or equal to 0. So when we solved this thing and we got y equals plus or minus the square root of x, that would have told us to pick the negative one, wouldn't it? See what I'm saying? Isn't that cool that it works that way? Okay, so let's do a problem like that. If you can do this, is by far the hardest stuff. You can do this, you got everything totally taken care of. Okay, so let's find two inverse functions. Okay, what if we've got, let's start off with f of x equals negative x cubed. Okay, what do I do to find the inverse here?
Put it in the y.
Okay, put it in terms of y. So y equals negative x cubed. Now what do I do? Cube root. Oh, I'm going to flip them. So I get x here, negative y there. Now what?
Cube root.
Not yet.
Multiply by negative 1.
Okay, good. I got to multiply or divide by negative 1. So I get
Divide.
y cubed equals negative x, and now
Cube root.
cube root. So y equals the cube root of negative x. Now a cube root, now this one, is there any problem with when I take a cube root of both sides, do I need a plus or minus?
No.
Yeah.
No, I don't. I don't, right? And so if I take, that means that this time I don't have any issues. If I were to graph this one, my original would have just looked like this. That is y equals negative x cubed. So what is my inverse going to look like? Well, if here's the line y equals x, now imagine this. If we take this thing and rotate it 90 degrees, so it kind of looks like this, right? And then I flip that around the x-axis, don't I just get something like that? Oops. Don't I just get something like this,
So you know how I do?
right?
That's a lot of snakes.
Right? Okay, my point being,
Looks like DNA.
my point being that this is an okay answer. I don't have to worry about, because it's, both of those are functions, aren't they? Right? Both the original blue and the final red functions both pass the vertical line test because the original blue function passed the horizontal line test, right? Now, why was this one so nice and the other one so ugly? Because that was an odd number. We took an odd root, right? But now what's going to happen here? Let's look at one more. What if we start with an even root? What if we have f of x equals, let's just do something easy like 4x to the fourth, but we're going to define this for x is less than or equal to 0. Okay? So now let's find the inverse. What do we do?
Change it to y.
Change it to y. So that becomes y equals 4x to the fourth for x is greater than or equal to 0. Now if I flip the x's and y's, this becomes an x, right? And so I have to deal with that too. What's that become?
Y.
Y is
Less than or equal to 0.
less than or equal to 0. So if I solve for y, what do I do?
Divide by 4.
Divide by 4. So then what does y equal? How do I get y by itself?
You double square root it.
Well, what do you do to undo a fourth power? This is what we, I take a fourth root, right? I take a fourth root of both sides. So y equals, I'll put the y over on this side. Y equals the fourth root of x over 4. But what am I missing?
There's minus sign.
Plus or minus. Because this is even, I have to have a plus or minus. But if I know that y is less than or equal to 0, which of those two am I keeping?
Minus sign.
Yeah, because y is less than or equal to 0, that's telling me that my answer has to be negative, right? And so that means I'm keeping that. And so my answer becomes y equals minus fourth root, that's about fourth root,
That's so cool.
minus the fourth root of x over 4,
This is like Einstein's.
right? Okay, see how that works? So that was that didn't seem like much at the beginning, but it actually was important. That's what provided us with that minus sign at the end. Okay? Make sense? All right, so real quick, if you look at this, just like you would expect, we make it y's and x's. To solve for y, flip the x's and y's, we get plus or minus the square root of x. And then here are our graphs. Now, as long as the original is defined only for x is greater than or equal to 0, there are our two graphs, right? Okay? If we look at the graphs of these power functions, these are the ones we looked at. If f of x equals x squared, there's the original blue one. We showed that the inverse of that is going to be this sideways parabola, okay? If we graph y equals x cubed, there's the original blue, there's the final red. Okay. Notice that that the inverse of x squared is not a function, but the inverse of x cubed is, right? Okay. If we restrict the domain and say only positive values of x, then we can, so we cut off the original left side of the parabola, that cuts off the bottom of the inverse, and then we're okay, right? If we restrict it, but if we don't, those aren't functions. So the graph of f of x can be intersected twice with a horizontal line. That's what we said then. That means that the graph of the inverse can be intersected twice with a vertical line. And so that gives us that horizontal line test. And this is, we did all this stuff. This is up there on the PowerPoint if you want to click through it again at home. But this is essentially what we just did.
Easy solution limits.
Okay, so there's our horizontal line test. If no horizontal line intersects the graph of a function more than once, that's the horizontal line test, then we know the inverse is a function. It's going to pass the vertical line test. Okay, so the assignment on this one, it's not a big deal. I really made it pretty short.